Artificial neurons on silicon chips, also known as neuromorphic chips or neuromorphic computing, are specialized electronic circuits designed to mimic the behavior and functionality of biological neurons in the human brain. These silicon-based neural circuits aim to replicate the parallel processing, energy efficiency, and cognitive capabilities of the human brain. Unlike traditional computing architectures, which rely on sequential processing and binary logic, neuromorphic chips attempt to emulate the brain's massively parallel processing by utilizing interconnected networks of artificial neurons. The design of artificial neurons on silicon chips involves creating circuits that can receive, process, and transmit electrical signals in a manner similar to biological neurons. These circuits typically incorporate various components such as transistors, capacitors, and resistors to mimic the behavior of neurons and synapses. Neuromorphic chips offer several potential advantages over conventional computing systems. They can perform tasks such as pattern recognition, sensory processing, and decision-making more efficiently and with lower power consumption. Additionally, the parallel nature of neuromorphic computing enables faster processing of complex data and the ability to adapt and learn from new information. Various research institutions and companies, including IBM, Intel, and Google, have been involved in developing neuromorphic chips and exploring their applications in areas such as artificial intelligence, robotics, and neuromorphic engineering. While the technology is still in its early stages, it holds promise for enabling new computing paradigms that can better emulate the brain's capabilities.